Hi, I am Arpit Maurya from IIT Ropar, India. This is my recent work on the differential representation for Carrollian correlator. I have derived the differential representation for Carrollian correlator by taking the flat limit of the ADS. Alternatively, we have used the property of Carrollian conformal primary wave functions, and we have derived the differential representation from Carrollian point of view. In this approach, exchange between diagram is obtained from the contact between diagram by acting the differential operators on it. The differential operators are the non-local combination of the ADS boundary conformal generators. Further, I will review the differential representation for ADS boundary correlators in emitting formalism. And we have shown that the 4-point SNL Witten diagram can be written in terms of the 4-point contact Witten diagram on which the differential operators will act. In doing so, we have used two facts that the ADS Laplacian can be written in terms of the ADS bulk isometry generators, and the second is the conformal word identity, which gives the relationship between the bulk isometry generators and the conformal boundary generators. Then we have discussed then we have derived the differential representation in global ADS coordinate. This is the crucial step for later section when we will take the Carrollian limit. And in this case, the conformal word identity will have some extra factor. This is because when we do the bulk isometry transformations and the conformal boundary transformations, bulk to boundary propagator scales up to some Jacobian factor. In the embedding coordinate, this Jacobian factor is 1 because the conformal transformations uh, is linear, but in the case of global ADS coordinate, the conformal transformations is no longer linear. So that's why Jacobian is not unity. So to find out this extra factor, we will do the conformal killing vector analysis, and by solving the conformal killing equation, we can find out the xi AB for different generators. Now I will discuss the flat limit of the ADS, and we will see that the in large ADS radius limit, uh, bulk of ADS maps to the bulk of the Minkowski space-time, and the boundary of the ADS maps to the null infinity of the Minkowski boundary. Further, the flat limit of the bulk to boundary propagator turns out to be the Carrollian conformal primary wave functions. Then I will discuss the differential representation for Carrollian correlator, and we will see that the large ADS radius limit of the ADS isometry generators and ADS conformal generators um, uh, uh, scales have leading order generators, which can be identified as a translation generators, leading order bulk generators, and this is the leading order boundary generators. Again, the identity will have some extra factor which can be found doing the uh, conformal killing vector analysis. Here we are interested only the translation generators because the Minkowski Laplacian can be constructed from the translation generators. This is the Carrollian differential representation, mathematical structure of the Carrollian differential representation analogous to the ADS case. In this case, the endpoint scalar Carrollian correlator can be obtained from the ingoing and outgoing Carrollian conformal primary wave functions, and we will see that the differential representation of the ADS correlator tells us that the Carrollian correlators are the modified Mellin transform of the flat space scattering amplitudes. Here we have derived the differential representation from Carrollian point of view. This is the translation invariance of a conformal primary wave functions. Doing the Taylor expansion with respect to translation parameters, we obtained this expression. This is the exactly the differential representation for the Carrollian correlators. At the end, for the consistency check, we have shown that if we add the differential operators on the contact Carrollian correlators, we will get the exchange Carrollian correlators, which exactly matches with the result available in some other literatures. And in this way, our differential representation is correct.